The third algorithm, let us find the total number of execution steps in the matrix addition algorithm. Matrix add, parameters are A array, B array, C array, then m comma n. So, assuming right the matrices A and B are of dimensions m and n, m by n, the resultant matrix C is obtained by adding the two matrices A and B, so that the order of C is of same as that of A and B, m by n. So, writing the algorithm here, for I is equal to 1 to m do, then for j is equal to 1 to n do. Writing the assignment statement, Cij is equal to Aij plus Bij, inner for n's here and for outer for n's here and for opening curly brace closes here. This is the end of matrix add, end of matrix add algorithm. Now, let us construct the table. A table headers, algorithm, then step per execution, frequency, last column step per execution into frequency. Constructing the columns, now consider the line. The first one, algorithm matrix add A array, B array, C array, m comma n. This is the name of the algorithm, right? So, first line putting dash, frequency dash, product column dash, then comment line C is equal to A plus B, putting dash, then opening curly brace dash dash dash. Now, consider the for statement, for I is equal to 1 to m do. We have already explored, right, in the for loop, for I is equal to 1 to n is executed for n plus 1 times. There the conditional test to be made is I less than or equal to n. Here clearly checking if I less than or equal to m, this is a conditional test. This takes one step per execution because a count is incremented by 1 for each step per execution or for each conditional test I less than or equal to m. So, step per execution for this a conditional test I less than or equal to m is 1. Likewise, for j is equal to 1 to n do, in which the main condition to be tested is j less than or equal to n. question mark. Check if j is less than or equal to n. This is tested, which may result in a true or false. Consider the inner loop. For j is equal to 1 to n do, the condition to be tested is j less than or equal to n. Checking if j less than or equal to n is taken as one count increment. So, the step pair execution for inner for loop is also 1. Then consider this assignment statement Cij is equal to Aij plus Bij. Simple assignment statement taken as one step pair execution. N for putting hyphen, then second n for hyphen, closing curly brace hyphen. So, considering the three statements, outer for, inner for, and this assignment statement Cij is equal to Aij plus Bij. In the outer for I is equal to 1 to m, the condition to be tested is for I is equal to 1 to m do. Condition to be tested is when I is equal to 1, it checks if I less than or equal to m. When I is equal to 2, it checks if I less than or equal to m. I is equal to 3, it checks if I less than or equal to m, etc. When I becomes m, same condition is tested if I less than or equal to m is true. When I becomes m plus 1, it also checks if I less than or equal to m. So, the step pair execution executing I less than or equal to m, this is one program step, count is incremented 1. So, I less than or equal to m, this condition test is tested for how many times? M plus 1 times. I less than or equal to m, this is tested for 1, 2, 3, etc. m plus 1. So, totally it is tested for m plus 1 times. So, here I is equal to 1 to m, the frequency is m plus 1. Understand? For I is equal to 1 to n means for I is equal to 1 to n do, the frequency is n plus 1. You have to remember this. Now, consider the inner for loop. For j is equal to 1 to n do. How many times this condition is tested? J less than or equal to n. Let us explore. Outer for loop is for I is equal to 1 to m do. Second for loop is for j is equal to 1 to n do. Consider the condition j less than or equal to n. Checking if j less than or equal to n is taken as one step pair execution. This is one step pair execution. The condition j less than or equal to n is tested for n plus 1 times. How? When j is equal to 1, checking j less than or equal to n. J is equal to 2, j less than or equal to n, a check is done. J is equal to 3, j less than or equal to n is also to be tested, etc. j becomes n, we need to check if j is less than or equal to n. When j becomes n plus 1, we should also check finally if j is less than or equal to n. So, checking if j less than or equal to n is one step per execution. How many times the expression, right, the conditional test j less than or equal to n is tested, right. So, clearly 1, 2, 3 etc. n plus 1, n plus 1 times j less than or equal to n, this conditional test is executed. Clearly, this inner for loop for j is equal to 1 to n do, this takes n plus 1 times execution of the condition j less than or equal to n. And this inner for, this is controlled by the outer for. Outer for executes the inner for. Outer for conditional test is done for m plus 1 times I is equal to 1, 2, 3 etc. m plus 1. But when I becomes m plus 1, the condition m plus 1 less than or equal to m, that is I is equal to m plus 1 less than or equal to m, this is false. So, that control comes out of the outer for. How many times the part of outer for is executed? The part of outer for is executed for just m times when I ranges from 1, 2, 3 etc. m. So, the part of outer for is executed for m times execute this inner loop. So, the logical concept is execute the inner loop m times. If one time the inner loop is executed, we have the conditional execution of j less than or equal to n, program step one program step is n plus 1 times execution. Since the inner for is controlled by the outer for, which is going to be executed, that means the inner for is going to be executed for m times. So, clearly the conditional test j less than or equal to n is tested for m into n plus 1 times. This is important. J less than or equal to n is tested for m into n plus 1 times. Since inner for loop is tested, condition is tested for n plus 1 times, inner for loop, right, is controlled by the outer for loop for m times. So, finding the product m into n plus 1. So, m into n plus 1 times the condition j less than or equal to n is tested. Hence, here j is equal to, for j is equal to 1 to n do, what is the frequency? The associated frequency is the product of m and n plus 1, m into n plus 1. Likewise, the assignment statement Cij is equal to Aij plus Bij takes an execution of m into n times, because outer for loop, right, this is m times inner for loop, right, j is equal to 1 to n, part of inner for loop is executed for n times. So, this is executed for n times, but outer for is executed for, part of outer for, right, is executed for m times. So, finding the product, this is simply m into n, mn times the assignment statement is executed. Now, let us find the last column, finding the product, right, 1 into m plus 1, this is m plus 1, second for, this is mn plus m, the assignment statement takes an execution of mn frequency. Finding the total, adding the last column, we have mn plus mn, mn plus mn, 2mn plus m plus m, 2m plus 1. So, clearly a 2mn plus 2m plus 1 steps are there in the execution of matrix addition algorithm. So, concluding, T matrix add, T matrix add, the problem instances are m and n, because the dimension of the matrices A, B, C are m by n. T matrix add, T, right, time complexity notation, matrix add algorithm name, m and n problem instances, problem instances, T matrix add m comma n is equal to 2mn plus 2m plus 1, a 2mn plus a 2m plus 1. The same count 2mn plus 2m plus 1 is obtained using the step count method. We have already applied the step count method in finding the total number of execution steps of matrix addition algorithm. There also we have obtained the same result, 2mn plus 2m plus 1, which results in theta of mn computational complexity. So, the step table method, which finds the total number of execution of the matrix addition algorithm as 2mn plus 2m plus 1 steps easily, right, compared to the step count method. Now, let us apply the step table method in finding the total number of execution steps of finding the nth Fibonacci number. Nth Fibonacci number. So, writing the algorithm here, algorithm, name of the algorithm is, for example, Fibonacci, parameter is n, that means we need to find the nth Fibonacci number, assuming the sequence is 0, 1, 1, 2, 3, 5, 8, 13, etc. When n is equal to 1, we need to find the first number is 0. When n is equal to 2, the second number is 1. N is equal to 3, the next number is 1. This way, right, we need to find the subsequent numbers. writing here the assignment statement. A is equal to 0, B is equal to 1 for I is equal to 3 to n do C is equal to A plus B, A is equal to B, B is equal to C, and for then return a value C, closing curly brace. This is end of Fibonacci. The algorithm finds the nth Fibonacci number. Putting n is equal to 1, the value 0 is returned, n is equal to 2, 1 is returned. So, assuming that we are going to put the value of n which is greater than or equal to 3. So, that having the initialization A is equal to 0 and B is equal to 1, I starts at 3. That means when I becomes 3, the third number is obtained. Third number is C is equal to A plus B. Then A and B are updated, A is equal to B, B is equal to C. For ends here n for, then the value of C is returned. Suppose n is equal to 3, I is equal to 3, 3 to 3, right, C is equal to A plus B, 0 plus 1, 1. Even A and B are updated to find for the next Fibonacci number. Then I becomes 4, control comes out of R, return C, C is right 0 plus 1, 1, 1 is returned. So, that this 1 is the third number in that sequence, right. So, assume n should be greater than or equal to 3. Now, let us apply the step table method to find the total number of execution steps in determining the nth Fibonacci number. First column algorithm, second column steps per execution, third column frequency, last column step per execution into frequency. Now, constructing the columns. First line write dash, second dash, third dash, 1, 2, 3. Now, A is equal to 0, B is equal to 1. This is taken as right simple assignment statements. So, A is equal to 0, 1 step per execution, B is equal to 1, 1 step per execution. Then for I is equal to 3 to n, in for I is equal to 3 to n, we need to check if I is less than or equal to n. Checking if I less than or equal to n is taken as 1 step per execution. Then C is equal to A plus B, right, 1 step, A is equal to B 1 step, B is equal to C 1 step. N for hyphen, return C, right, 1 step per execution, closing curly brace hyphen. Now, construct the frequency column. A is equal to 0, right, 1 time execution, B is equal to 1, 1 time execution. For I is equal to 3 to n, in the for loop, right, the condition to be tested is I less than or equal to n. In general, for I is equal to 1 to n, right, executes for n plus 1 times. For I is equal to 1 to n do. The condition to be tested is checking if I less than or equal to n. This is executed for n plus 1 times. When I is equal to 1, 2, 3, etc., n comma n plus 1. That is what we have, n plus 1 times. Here, based on the logic, right, we have designed, since we need to find the nth Fibonacci integer, initial value of I starts at 3. So, I is equal to 1 is ignored, I is equal to 2 is ignored. So, totally n plus 1 times or 2 values are missed. So, n plus 1 minus 2, this is equal to n minus 1 times, clearly the for loop is executed. What is the for loop? For I is equal to 3 to n do. This is tested for n minus 1 times. Total time for I is equal to 1 to n is n plus 1 times. Twice, right, the values of I, that is I is equal to 1 and I is equal to 2 are skipped here. So, starting from 3 to n plus 1, we have the execution of n plus 1 minus, right, deducting the 2 times, we have n minus 1 times. So, putting here for I is equal to 3 to n, the execution is n minus 1 times, writing here this is n minus 1. If the for condition is tested for n minus 1 times, clearly these are the part of for, the part of for is executed one less than the for loop execution. So, this is n minus 1 times execution. Clearly, the part of for is executed for n minus 1 minus 1 time execution, that is n minus 2 times execution. So, I am writing here this is n minus 2, this assignment statement also n minus 2, B is equal to C also n minus 2, n for hyphen, return C one time, then last one hyphen. Finding the product of these two columns, step pair execution and frequency, we have 1 into 1, 1, B is equal to 1, this is 1, I is equal to 3 to n, 1 into n minus 1, n minus 1, these are n minus 2, n minus 2, n minus 2, hyphen 1, then hyphen. So, the last column is constructed the product of step pair execution and frequency. Finding the sum, right, we have 1 plus 1, 1, 2, 3, this is n minus 1 plus thrice n minus 2, 3 into n minus 2 plus 1, 1, 1, right, 3. So, total time execution is T Fibonacci of n, this is equal to finding the nth Fibonacci number. Computational time is represented as T Fibonacci, n represents the problem instance nth number, n minus 1 plus 3 into n minus 2 plus 3. So, the total computing time of finding the nth Fibonacci number is given by a T Fibonacci of n, a T Fibonacci of n, n represents the problem instance, characteristics. That means finding the nth number in that sequence, a T which indicates the total number of execution steps. Adding the last column, we have the expression n minus 1 plus 3 into n minus 2 plus 3, n minus 1 plus 3 into n minus 2 plus 3. So, simplifying this n minus 1, 3n minus 6 plus 3, 3n plus 1n, right, 4n, minus 6 minus 1 minus 7, minus 7 plus 3 minus 4, this is 4 into n minus 1, n minus 1 plus 3n minus 2 plus 3, right, simplifying this 4n minus 7 plus 3, 4n minus 4, so 4 into n minus 1, that is t Fibonacci of n is equal to 4 into n minus 1. So, the total number of execution steps in finding the nth Fibonacci number algorithm is 4 into n minus 1. This is 4n minus 4. This results in theta of n, a linear computational complexity. A linear computational complexity. So, using a step table method, we have obtained the total number of execution steps of the finding the nth Fibonacci number algorithm is 4 into n minus 1. If you apply the step count method, right, what we have to do, we need to set a global variable count here, count should be initialized to 0 for each executable statement. Whenever we have a program step, we need to increment a count by 1. So, introducing the proper count statements here, right, we will have the same result, a t Fibonacci of n is equal to 4 into n minus 1, which results in a theta of n, a linear computational complexity.